Hey everyone, so we're going to continue our discussion about kinematics and in particular about vectors. So we talked about how with vectors, vectors care about direction. What happens if we have multiple vectors of, let's say, displacement or multiple velocity vectors? How do we end up handling that? With scalars, that's easy enough. You just add the numbers. You move 5 meters left, 10 meters to the right, you have 15, easy peasy. But what about when they're vectors? And we want to find the final vector. So first, one thing to keep in mind is that when you when you combine multiple vectors, two or more vectors, we end up calling that final sum the resultant vector. So it's the results of all those movements. And this is true for any type of vector. We're going to mainly focus on displacement because that's what we've been talking about so far, but this is true for any vector. Now, there are two different ways that we can add vectors together. The first is the tip to tail method. Now, I do want to point out is that this is mainly a regions thing. So, I will mention this, but it's only really going to play a part when we start reviewing for the regions exam. However, it is still important to note because there's a chance that you might end up seeing it when you start going off to college. So just keep that in mind. The tip to tail method is essentially drawing it out. Because the vectors can be represented by arrows, what we end up doing is drawing arrows relative to their values, proper scaling, and we draw it out so that we can actually pinpoint where our starting and ending position is. We are essentially making a treasure map, and we make it so that each arrow starts where the next one ends, and we keep going that way. All right. So here's a perfect example. Let's say you were traveled 5 meters east, 10 meters west, and then 3 meters east, and you want to know your displacement. Now, most of you probably could figure it out without doing this, but this is just a simple example. So the first thing you'd have to do is represent whatever the scale is. That depends on the paper. Here we're going to just say 1 centimeter equals 1 meter, but you might have to do something else. Then you pick your point or you use whatever point they give you. And then you draw out those three directions, 5 meters east, 10 meters west, and 3 meters east. Then what you would do is you would draw a line going from the start to final position. This one is not drawn to tip to tail because it's the resultant, it's something else. And then you would measure that, and using our scale, we'd figure out what that was. So for example, in this scenario, it's pointing to the left, so that's west, and it's 2 centimeters long, so it's 2 meters. So I know my displacement is 2 meters west. I can also do it in 2 dimensions. This actually makes it really easy. You just draw the arrows, you draw a line going from start to finish, and then you measure the line with a ruler and use your scale to figure out what it is in meters. You can also use this to figure out the angle at which it's working at. So, you know, keep that in mind. Now, there is a second way to do it, as I mentioned, using math. Now, in some cases, in the simpler cases, this method works really well. But when we start using more complex arrows, it gets a little bit trickier. Basically, the thing to keep in mind here is that we're going to assign a value, a sign value to the different directions. I mentioned before that vectors can either be positive or negative. If they go to the right because of the x-axis, right is usually seen as positive, left would be seen as negative. So we would do that same thing here. West would be considered negative because that's typically the left side, and then east would be positive, north would be positive, and south would be negative. So the first step is to group like directions because you can actually combine north and east together, or south and east, or left and north. So you have to actually group the like directions. North and south go together, east and west go together, left and right go together. Then you actually have to define positive and negative. Now, the reason why I say you define it is because technically it doesn't really matter what direction is positive and negative as long as you're being consistent. Now, if you want, you can make it so that anytime you do north, east, right, or up, those are always positive numbers, and south, west, left, and down are all negative numbers. However, sometimes you might be doing a scenario where that's not the best case. For example, if you're doing a projectile where you are launching something off of a tall building and it ends up going down, you might want to define going down as being positive. It really depends on the scenario, and that's something you'll see me fooling around with a lot in our practice problems. The next step is that you just add up the numbers. So after you group them and you define positive, negative, you just add the numbers in that group, and the resulting sign tells the direction. Now, there is an extra step of what happens when we had a group of north and south and a group of east and west. How do we combine those two numbers into a single value? And I'll mention that later on. So if we use the same scenarios before, what we would say is, well, I have 5 meters and 3 meters are both east, so those are two positive numbers. 10 meters is west, so that's going to be negative. I add those three numbers, 5, negative 10, and 3, and I get negative 2. So I would know that my displacement is 2 meters west because the negative symbol. Uh, that's pretty much it. Now, what happens in 2D? Like I said, we end up with the same thing. You combine the north and south, you combine the east and west, you do the same thing. But here, what we end up having is we can't combine the east direction and the north direction the way it is because of the fact that they aren't in the same dimension. They're perpendicular to each other. So when we draw it out, you can already see what we're going to end up having to do. We're going to have to do a Pythagorean theorem. We've made a little right triangle with the x direction being my horizontal side, the y direction being the vertical side. So now I do a squared plus b squared equals c squared, and then I end up getting that this hypotenuse is 12.8 meters. And then I could also use SOHCAHTOA to figure out the angle. Here I'm using tangent, and I would get that the angle is 51 degrees. Exactly the same thing I got in my picture before. Now, what if we had more complex vectors? What if they gave us this scenario where we had these two vectors at weird angles? How would we find this? Again, there's two different ways of handling this. The first one is doing law of cosines. You might have remembered this in your previous math classes. It looks very similar to Pythagorean theorem, but it has this little extra 2ab cosine c factor in here. What you would do is pretty much similar to Pythagorean theorem. You do a squared 8 squared plus 5 squared, but the c in this case would be this angle right here. So in this scenario, I'd have to do 180 minus 53, find this angle, plug it in, calculate, bada bing, bada boom, you get 11.7. Now, the second way to do this one is actually the way that I would probably do it, only because of some of the other things that we're going to be doing. What you can do is take this arrow and break it up into what's called its components. So you break it up into this x and y component. So do SOHCAHTOA again with the 53 degrees and the 5 meters to get that this is 3 and 4. And now what we have is one giant right triangle. So we have 11 as our base and 4 as the height. We could do a squared plus b squared pretty easily, get 11.7, and we could do the angle to get 20 degrees. So that's the other way to deal with these complex vectors. Now, for the most part, as I mentioned before,